Hello dear students, I am Dr. Moinuddin. In this video we are going to discuss about inductively coupled plasma atomic emission spectroscopy. It can be abbreviated as ICP-AES. We will discuss this technique in detail. So today there is part 1 of this technique. As you know, we have already discussed flame emission spectroscopy, in which we have discussed about emission phenomena, and we have seen the technique of emission spectroscopy by using the source of atomization, and that was flame. What is the difference between flame photometry and ICP-AES? So that the difference is the source of atomization. So here the atomizer will be inductively coupled plasma, which is actually our topic. We will discuss it in detail. And here are the contents of current video. So actually it is the basic introductory lecture about this technique. So we will see the basic introduction of the technique, and then we will see the principle of operation, that how it works. So let's get started. So first of all, introduction. Inductively coupled plasma atomic emission spectroscopy is an analytical technique for elemental detection. So this is the technique basically which is used for elemental analysis. So it is the type of atomic spectroscopy, or we can say it is the type of atomic emission spectroscopy. So the basic phenomena is the emission phenomena. It applies to all elements except argon. So by using this technique, we can detect almost all elements except argon, because argon gas is usually used for the production of plasma. That is why it can also be abbreviated as ICAP, inductively coupled argon plasma. Then sample may be introduced as liquid, gases or solids. So we can introduce sample, and our sample may be in any state. It may be solid, liquid or gas. So definitely we must have to change the sample introduction system. Usually samples are introduced in liquid form as aqueous solutions, but generally the samples are introduced in the form of liquids, and actually they are in the form of solutions. Maybe some organic solvent or aqueous solutions can be introduced in this technique. Using this technique, we can analyze approximately 70 elements with detection limits up to parts per billion level. So by using this technique, we are able to analyze more than 70 elements, and we can detect more than 70 elements simultaneously. And even if these elements are present in very minute quantity, means we can detect these elements in the sample even if they are present up to parts per billion level. It is an important technique in modern analytical laboratory. So the importance of the technique cannot be denied in modern analytical laboratories, as it has found a large number of applications in various fields, like in metallurgical fields, where we may be interested in analysis, in qualitative and quantitative analysis of various elements obtained from the ores, then various geological processes, then various environmental samples in which we might be interested in analysis, in calculation of various quantities of various elements in environmental samples, then in agricultural field, industrial field, and in biological fields. So it's been widely used in different fields. The first developmental research on the ICP as an excitation source for optical atomic spectroscopy was published in 1964. So first research was published actually in 1964, and then the first commercial instrumentation began to appear in the market in mid-1970s, which regenerated the interest of researchers in emission spectroscopy. So by the appearance of the instrument in around 1970s, which was actually somewhere 1974, the technique became much popular. The popularity of the technique was due to its ability to perform multi-elemental analysis. Means, by using this technique, we can measure a large number of elements. We can analyze a large number of elements in the sample simultaneously. And these elements can be determined up to a wide range of concentration. So, due to these reasons, the technique became much popular. These characteristics were found missing in atomic absorption spectroscopy, because in atomic absorption spectroscopy we can't perform multi-elemental analysis simultaneously, because for each time or for each element we have to replace the source of radiation, which may take a lot of time. So that's the time consuming technique. So that's why this technique became much popular. Moreover, the high temperature and an inert argon atmosphere of the plasma also lessens the various interferences generated in flame atomic emission spectroscopy. In flame photometry, the source of atomization is flame, and the temperature of flame is not much high as compared to the plasma, which is too much high. So due to high temperature and inert argon atmosphere, the chances of generation of various interferences, these are very much reduced. So this is also another advantage of the technique. Then after introduction, we will see the principle of operation. Different plasma sources exist, but most common is inductively coupled plasma. So there are various types of plasma which can be used, but most common one which is used in this technique is inductively coupled plasma. Inductively coupled plasma, actually it is an excitation source for atomic emission spectroscopy, and it is an argon plasma. Means the fuel for the generation of plasma is argon gas, and this plasma is operated at an atmospheric pressure, and it is sustained by inductive coupling to the radio frequency electromagnetic field. So the plasma is generated by the use of argon gas, and it is sustained by to sustain it, the system is coupled to the radio frequency electromagnetic field. Argon gas flows axially through a quartz tube. So this is actually we are talking about the plasma torch, through which argon gas flows axially, and this torch that is surrounded by 3 to 4 turns of an induction coil, and this coil is connected to a radio frequency generator. The standard frequencies at which the radio frequency energy is normally supplied, so this generator normally works at the frequencies which are 27.12 megahertz, or less commonly it is 40.68 megahertz. And by the use of these frequencies, it generates the power output between 0.5 to 2 kilowatt. These standard values are set by an organization named Federal Communications Commission for Scientific and Medical Instrumentation. And here is the diagram we can see. So this is the plasma torch, and we can say this is the outer wall of plasma torch, which is made up of quartz. And these three dots on the left and right, actually these indicate the induction coils. So three dots mean there are 3 turns of induction coil. So the high frequency current of up to 100 ampere flows in the water cooled copper induction coils. So through these coils 100 ampere current flows, and these coils are made up of copper, and these are actually the water cooled copper induction coils. So when this current flows, so it generates oscillating magnetic fields whose lines of force are oriented axially inside the quartz tube and follow closed elliptical path outside the tube. So this actually indicate the magnetic field whose lines of force are oriented axially inside the quartz tube, and these follow the closed elliptical path. So you can see this one is the closed elliptical path. So this is actually the magnetic field. If free electrons are present inside the tube, so here are the free electrons which are present inside the tube, and usually these are generated by the use of some spark source. So the induced magnetic field causes the electrons in the gas to flow in oscillating closed annular paths inside the quartz tube. So if free electrons are present inside the tube, so this magnetic field actually it causes the electrons to flow in oscillating closed annular paths like this inside the quartz tube. And we can see here is the argon gas flows, and through here we can generate a discharge to generate the free electrons inside. So the flow of these electrons inside the quartz tube, it's termed as eddy current. These electrons are accelerated by the time varying magnetic field, which causes collisions and results in further ionization of argon, further generation of plasma, and resistive heating as well. So we can conclude that actually these electric and magnetic fields, so actually these are responsible for generation of plasma. As argon is initially neutral, so initially definitely the gas supplied inside the tube, so that is neutral and it's non-conducting, the plasma must be initiated by the seed electrons. So to initiate plasma we require seed electrons, which I already mentioned earlier as free electrons, and these are generated by Tesla discharge. With radio frequency power applied, plasma ignites instantaneously and then it is self-sustaining. So the resulting plasma is a highly ionized gas with temperature range 8,000 to 10,000 Kelvin. So this is too much high temperature, 8,000 to 10,000 Kelvin, and we can say it is the temperature of the surface of the sun. So the temperature of the plasma is very much high. Plasma mainly consists of following species. So we can expect which species could be present inside. So there could be the neutral argon atom. There could be the ionized argon species. These species could be present inside. There could be some of the neutral atom, and they may be in excited state, so excited argon could be present. And some ionized, some of the ionized argon, they may also get excited, so there could be the excited ionized argon. And some of the argon atoms, they may exist in metastable state, so they may be present. And there could be present the free electrons. So the mixture of all of these species, so it is actually the plasma. And here's the photograph of plasma. So how it looks like, you can see clearly. Here are the induction coils, and here is the plasma. So dear students, this was all about the part 1 of inductively coupled plasma atomic emission spectroscopy. Hope you did understand it, but still a lot more to come. So if you like this video, then like it, and if you didn't subscribe my channel yet, then subscribe it right now to get in touch with my upcoming videos. So thanks for watching. Thank you very much.